All right, now let's start with this expression. So one thing we can do is get rid of the rho and use the differential form of Gauss's law. Del dot E is equal to rho over epsilon 0. So I can get rid of rho and write this as half volume integral del dot E times V d tau. Okay, now this looks very similar to our expression, the left-hand side of our integration by parts formula. So we had del dot a vector with multiplied by a scalar function and the volume integral of that, and that was equal to this right-hand side. So that's what we'll do over here. So this is going to be half volume integral, actually negative half volume integral E dot gradient of V. Remember, gradient of V is a vector, so we are taking the dot product of that with E d tau plus surface integral V E dot d A, and this surface integral is evaluated over the boundary of the volume that we're using. All right, now we're almost done. We can do one thing right now, which is we can use the fact that del dot V is equal to minus E, or minus del dot V is equal to E. This is something that we had seen in class, that the electric field is the gradient of the potential. Actually, this shouldn't be, V is not a scalar, so V is a scalar. Gradient of V is equal to minus E. Plug that in. Half, and did I forget an epsilon 0? Yeah, so there should be an epsilon 0 here. So you have E dot E d tau plus V E dot dA tau. And what is E dot E? E dot E is just the magnitude of E square. So, so when I did that, when I put del dot V for E, that produced a minus sign, which will cancel out this minus sign. So what we have is half epsilon dot E square d tau plus this surface term V E dot dA over the surface d tau. Okay, surface of the volume tau. All right, so now comes the really beautiful part of this proof. Now, what volume are we using here? So we had a certain charge distribution, right? And we are looking at the energy of this charge distribution. So clearly we can use the volume of the charge distribution itself, like this volume, as our volume of integration, because that would enclose all the charges. But there is no harm in taking a different volume, a larger volume. So I could have taken this larger volume as well, because it encompasses the same charges, and so we don't really care. So it doesn't really make a difference if we use the larger volume. So since we have the freedom to use any volume we want as long as it encompasses all the charges, uh, let's use an infinitely large volume. So suppose our volume, let's allow the volume over which we are integrating to be infinite. So infinitely large volume. And so we are using this mathematical trick that we are allowed to integrate over any volume as long as it encompasses all the charges. So why not use an infinite volume? The advantage of using an infinite volume is the following. Look at the surface term. look at the quantities in the surface term. So essentially we have a potential due to a charge distribution, an electric field due to the same charge distribution, and that is integrated over an area, right? So this second term is essentially uh, the product of a potential, an electric field, and an area. How do these things scale when the volume of integration is infinite? So the from far away outside a charge distribution, the potential will go as 1 over r approximately. The electric field will go as 1 over r square. And what does an area, uh, how does an area scale when you let the radius become infinite? So the volume of a sphere is 4 pi r square, so the area scales as 1 over r square, right? So you can tell how this integral is going to scale as you increase the surface, make the volume of integration infinite. It will scale as 1 over r. So this integral, this quantity, is roughly proportional to 1 over r. So that means if you choose a very, very large volume of integration, this surface will just go where the surface of integration is an infinite distance away, or r is an infinite distance away. This term will just go away, right? So if you integrate over all space, the total energy of the charge distribution U can be written as volume integral half epsilon 0 e square d tau, where the integration is now done over all space. What is this equation telling us? It says that if you integrate this quantity over all space, you get the total energy. And so that means that this quantity is the energy density. And you can see that the energy density is associated with electric fields. And so we've just proved that the energy density associated with electric fields is given by half epsilon 0 e square.